Graphs are of different types, and one method of differentiating between them is based on their directionality and their circulation. So we have directed graphs. Directed graphs are the one where each edge has some particular direction. Because the presence of an edge between A and B would suggest that you can access B from A, but not vice versa. At any point, if you need to say that A is accessible from C and C is accessible from C, then we need two separate edges or two separate connections between these two nodes. Okay. Most of the state transition models we have are of this kind. Then one other thing, these directed graphs need not be acyclic. ठीक है, तो ये जो complete cycle है, आप A से B पे जा सकते हैं, B से C और फिर, these are considered cyclic relationships. Starting from some node, you can have a complete path which will get you back to the same node. ठीक, these are cyclic transitions. The second category is directed acyclic graphs. So what are directed acyclic graphs? These are a smaller set, simplification of these directed graphs. These are still directed. The edges still have one direction, and it is not intuitive for one node to be accessed from both directions, given just one edge between them. But these do not support cycles. Okay? So you cannot end up with at the same node after traversing some path. So with the cyclic connections there, that is what we have gotten rid of, and we now call these directed acyclic graphs. The third category is undirected graphs. So if there exists an edge between A and B, we can say that A is accessible from B and B is accessible from A. Okay, so this simplifies things, and usually all type of connectivity networks are represented by this. Real geographical geographical maps, etc., are represented by this. So all of these are usually given by undirected graphs. If you remember, graphs are represented by adjacency matrix. So if I have this graph, I'll have all of the nodes placed as or labeled as rows, and all of the nodes labeled as attributes or columns as well. Okay? And every time there exists an edge between any of these two nodes, I'll place a 1 signifying the presence of that edge. Okay? तो एडजेसेंसी मैट्रिक्स से जब ग्राफ को रिप्रेजेंट करते हैं तो हमारे पास रोज में भी सारी नोड्स हैं, कॉलम्स में भी सारी नोड्स हैं, और उनका कनेक्शन रिप्रेजेंट करने का तरीका क्या है कि वी प्लेस 1. जहां पे भी 1 एग्जिस्ट कर रहा है कनेक्शन है, 1 एग्जिस्ट नहीं कर रहा है तो कनेक्शन नहीं. वेटेड, अगर हमने सेम डायरेक्टेड ग्राफ बनाना है लेकिन वेटेड बनाना है तो इंस्टेड ऑफ जस्ट 1 and 0 रिप्रेजेंटेशन, अब हम क्या काम करते हैं कि वी असाइन वेट्स टू देम. So an edge from B to A costs 3. ठीक है, from B to B, ये जो circular edge था, that costs 4. Because the only difference is that instead of having simple 1 and 0, या presence या absence, we now have the weights associated with them as well. Then we can also represent it in the form of an edge table. Instead of the adjacency matrix, now we have an edge table. और उसमें क्या है कि we have list of all of the edges. Every edge corresponds to one new row. So instead of a matrix, we now have a list, and the list has all of the edges of it. और अगर if we have weights, तो हमारे पास weights का एक अलग column बन जाएगा, and you will store the weights in there. And this is something this is easier to store in relational databases. Instead of that 2D representation, it is easier to store this list format, simpler table format in relational databases. And the adjacency list, just as we had adjacency matrix, we can also have adjacency list. फर्क क्या है? Simply put the number of nodes A, B, C, and one column represents all of the incoming edges and the other column represents all of the outgoing edges. So A is connected to B and C. A can be reached by B and C. So we have incoming edges B and C. Okay? Since A has no outgoing edge, so that's left C. Similar for B, B has a self circle, and then B can reach C. So B and C are the incoming edges of B, and A and C are the outgoing edges. And this helps, or this sort of representation is usually used in MapReduce implementations. So all of these representations are equally effective. We just need to see what application we are coding in order to understand, make a decision about which one to actually use. Looking at the graph model, a graph model consists of a set of vertices or these nodes and a set of edges or links between these two nodes. The important point is that in the label property graph model, or one which is one representation of graph, each element, vertex and edge has an identifier, has some label, and has a set of key value pairs or properties. Let's look at that in detail. Consider this node. This A node represents a person. Okay. So we've got the ID, unique identifier. We are calling it A. The label or the class or the type is person. Name or the actual data stored in it is Khaled. Age, profession. These are the attributes of the node stored over here. Then we connect it to another node. Now this is a B node. Again, it has a unique identifier B, and it has a label post. So note the first thing, that the first label is different from the other label, or let's say that these nodes are of different types. The first one was representing a person, where the second one is representing a post. Then these title and tags, these are inherent to here. These are the properties of the post itself. These are connected by person and post are connected by an edge posted. And this has properties of its own. It has an ID. ID is X, and this X lies between A and B. Okay. The label or the class or the type of it is posted, and its property is, its attribute is the date time. Now this person may be connected to another person. We're calling it C. It again has its own label, its own data, and it can be connected to, again, any number of other nodes. Okay? So this is the complete representation of the graph, where we've got a number of nodes that may be connected to any other number in a directed manner or undirected manner, cyclic or non-cyclic manner.